All right, so I've got two blog posts that I posted at my time at Whereabouts. The first one is change detection using Alpha Earth Foundation embeddings, which is actually a follow-up blog, and another one around zonal stats um, over fields of the world, looking at principal component analysis as those zonal stat points. So I'll start with change detection. I'm kind of ambitious. I'm trying to cover two things in 5 minutes, but I think we'll make it happen. So just to set the context, both of these blog posts are using the Global czar AEF mosaic that Jeff put up. It's on Source Co-op. You can access it this way. It's very, very large. It's a pixel-based embedding model, weighs in at about 3.8 petabytes, but there's only chunks that are present for areas that intersect land. And we're also using ZAR v3. So each of the chunks are actually sharded. So there actually aren't a billion chunks or 10 billion chunks or whatever this ends up being. We used a couple of roster flow tools behind the scenes at Whereabouts. This is a tool that I was working on while I was there to build a mosaic and to build ZAR multiscales for visualization. And this community has put a ton of work into multiscales to enable visualization, which we'll get to in a second. So in order to do change detection, and this experiment, I wanted to sub-select an area, the state of Colorado, over the ZAR AEF mosaic, and I decided to use the leave one out medoid approach in order to basically provide a score along the time dimension of like, is this pixel an outlier? Here's some math to sort of explain what that is exactly. But basically what you're doing is for each point in time, you're looking at the rest and you're calculating the medoid, which is basically the mean. It's the closest actual point to the mean. And you're taking the distance. In this case, we're using cosine distance between that point in time and that medoid, the held out set. This is sort of an out of distribution score. And so to quickly look at results, we basically get the same dimension in time band y and x, where there are two bands specifically for cosine distance over time, and then the leave one out medoid distance over time. We also normalized it in a previous blog post. I did not do normalization over time, which lent itself to really strange looking maps, and it was really difficult to compare like what was an outlier, what was not an outlier, because different areas across the map were on different scales. So in order to make pixels in across space kind of exhibit the same scale, we normalized. So that's what we did. In order to visualize, you built a ZAR multiscale, and you can see the data tree here that reduces dimensionality in X and Y as we go up the overviews. And finally, we get a map that allows us to sort of scan through and see change in Boulder. So the blog post kind of goes in more depth, but basically I can sort of scan through time and find when this new high school in Boulder was actually put up. And I can kind of scan through here and see that construction probably started in 2023. So there's change detection. All right, jumping scenes. 1 minute left. Using the same exact input, we built. I built on a little side project. It's called Raison. It's a GitHub project that I have going on right now. It's pretty simple. It's all ray based. So what it does is it takes in an arbitrary GeoParquet data set, and it does an embarrassingly parallel read any chunk once partial aggregate summary approach to build GeoParquet zonal statistics. We use fields of the world and basically join that and compute the mean AEF embedding for each field. And we had about 3.5 million fields. Running up on time, I got about 10 seconds. But basically what we are able to do is visualize once this loads, because it's pretty significant. Oh, there we go. We're able to actually look at the mean embedding for the zonal statistics over all the fields. So the colors here are actually the first three principal component analysis, or first three principal components of the AEF embedding, the mean AEF embedding for that entire field, which I thought was pretty interesting analysis. Anyway, I just wanted to put it out there that I think that this is a really great way to reduce the redundancy in data, as Isaac and Caleb both mentioned. All right, that's the time for me.